How awkward is the standing?
Like a 5 out of 10.
You know, you're
How
good.
do-
Go
how
ahead.
do we make it
That
worse?
was like 2 seconds.
Oh, are you?
You're good. You're good.
Okay. My name is Alan Thurman. I'm reporting on the Rankine cycle. So a little bit of experimental background for the Rankine cycle experiment. So the objective of this experiment was to explore the Rankine cycle, which is a vapor compression power cycle. The primary stages of the cycle are to pump water into a boiler, where it's then heated and turned into steam, and then the steam is piped into a turbine that turns the steam expansion into kinetic energy, and that outputs work. Then the outlet gases of the turbine are then fed into a condenser where it removes heat from the steam and then condenses it and is fed back into the pump, and then that creates a cycle. So you have an isentropic, isentropic compression? Yeah, isentropic compression, isobaric heating, and then isentropic expansion, and then, isobaric condensation. And then some of the key equations are down here. So the equipment, we have our lovely Rankine cycler trademark. So some notable subsystems are the computer with DAC software. You have your primary control panel with some manual readouts, as well as the pressure gauge for the boiler. You also have the steam emission valve, the load dial, and the water level sight glass, which is very important not to let that water level get below 1 inch whenever you're running the experiment. So some safety, be like Bobby, wear your safety glasses, long pants, closed-toed shoes. Compressed gases, so we're working with propane, which is a compressed gas that's also flammable, so you need to inspect all the equipment for leaks and damage before using it. And then do not exceed the safe operating range of the equipment, so don't put the output voltage above 10 volts and don't allow the boiler pressure to exceed 120 psi. That one's especially critical. And then when shutting down the Rankine cycler trademark, gradually reduce the speed on the turbine to not over rev the impeller, which could damage the equipment and be a considerable expense to the university. Procedure, so first you're going to drain the boiler and the condensing tanks and refill them, as well as inspect and connect the propane tank. So once you've refilled the boiler, you're going to inspect and connect the propane tank, ignite the boiler, ensuring that the steam emission valve is fully closed. Then you're going to do a preheating cycle where you allow the system to build pressure in the boiler until it's about 110 psi. We'll then slowly open the steam emission valve and to allow some flow through the turbine. And you're going to use the steam emission valve and the load dial to control the revolutions of the turbine and the generator to make sure that you're staying within the safe operating range of the equipment. You'll then allow the system to reach a steady state and data log for about 8 to 10 minutes. And then once that's completed, you will slowly turn off the boiler and then release the excess pressure in the manner that I stated earlier. So after performing this, we got some information from steady state. So these are the thermodynamic properties at all the points of data logging, and then also just kind of static temperature water that we use as the input to the boiler. So moving on to this is kind of hard to present on, but some of the performance results that we got from the thermodynamic data is the boiler heat input is about 39 kilowatts, the turbine work is about 3 kilowatts, and then the motor power generated was 9.7 watts, which is 0.0097 kilowatts, and so you can see the generator efficiency is quite low, about 0.3%. And then the calculated mass flow rate of the system is 0.03 kilograms per second, and then the total thermal efficiency was calculated to be about 8.6%. You can move on.
Higher than 5 out of 10?
Higher than 5 out of 10. So I think we skipped a slide now. Gotta love Microsoft Teams. Got all these softwares in it, they don't really integrate that well.
This happened to me during my capstone midterm, so if that makes you feel any better.
That's a lot worse.
Yeah.
Captain Dave.
I don't know, this
very
is worse
upset
than,
about
this is more important than catch on my turn.
Yeah.
this.
Captain Dave said, Adam, are you there?
Pretty sure everyone was sleeping during ours because we were last.
Hey, we were second to last.
Were we?
Almost there.
Come on.
Doesn't like
Do you have some animations on the next slide or something?
No. There we go.
There we go.
Okay, so here's some raw data of the boiler over the whole time span. So you can see from the fuel flow that we ran for about 300 seconds at steady state. I cropped it to about 280 seconds just to get kind of the best segment of data. You can see on the boiler temperature versus time, it's slowly decreasing. There's some noise there, but you can also notice in like the scale on the y-axis that it's fairly fine scale on the scale.
Oh no.
Oh no. Anyway, turbine raw data. So you can see that the turbine inlet pressure remains. Okay. So you can see the boiler.
The timing is just awful.
Just give it a couple of minutes and then restart it.
Okay.
Yeah.
Okay, so you can see the boiler pressure over time dropped a lot more, and I think this is just due to the slow reduction in volume within the boiler as the steam exits. Yeah. Too many colors.
I feel like this is my fault.
Yeah, we switched the extent part. Everything.
There we go.
Okay, so you can see turbine inlet and exit pressures remain fairly constant across the whole run, which is a good sign that we're at somewhat steady state conditions. The turbine inlet tip and exit temp are a similar story, both falling off after 300 seconds whenever we cut off. And then the next slide.
We definitely get a negative comment for this.
Okay.
Damn!
It's not his fault. Well, you throw some
It's all the camera, it's all Claire's
Did you
fault.
zip phone?
Okay, and then so we have also some information on the generator. So we were running at a fairly constant current and a fairly constant voltage. And as you can see, the turbine RPM is not that great. The y-axis there is wrong, but you can see that we kept it within mostly a 100 RPM range, but it was definitely not ideal. So we can go on to the next slide, talk about some conclusions from all this data. Eventually.
You can do it. I don't know why I say it's got it. There we go.
Okay, so you can see this picture of Penn Hill. So some applications of the Rankine cycle is responsible for generating 90% of the world's power. It was performed in this experiment, was far from the ideal cycle. And the inverse Rankine cycle is also the primary form of refrigeration. And the Rankine cycle is the cycle behind most steam engines. So we basically had a propane-powered steam engine, so I think the picture's fitting. And some notable sources of error. So we triggered the automated shutoff due to low water level, which meant that my mass flow rate for most of the power calculations was a bold assumption and probably incorrect due to like having the wrong volume associated with the flow rate. We also did not perform a full cycle because the working fluid is not recycled back to the boiler, which makes some of the math a little weird. We also did no measurements on the condenser's state, so those were all done as assumptions, just assuming that it's the same state or like ambient boiling. We also, so I assume the total volume in the boiler is 0 whenever the time that we said we stopped at was, but I think there was some extra time from when it shut off till the calculation. Also, the ammeter in the DAC disagreed with the ammeter on the instrument panel, meaning that the power calculated from the data in the CSV file is likely lower than what was actually being generated by the mower, which makes the efficiency look a lot lower, but I still don't think it was on the order of magnitude that we were seeing, so still relatively close numbers. And then it was also assumed isentropic turbine to find the quality of the steam exiting the turbine, which is probably not the best assumption, but it's what I went with on this. Anyway, any questions?
No.
Might be a micro